All right. Hello, everyone, and welcome to our department seminar. So today is my great pleasure to introduce Professor Kamalika Chaudhuri from UCSD. Kamalika is Associate Professor of Computer Science at UCSD. Her research is on the foundation of trustworthy machine learning. She has done many seminar and milestone works in privacy-preserving machine learning, learning under sampling bias, and also learning in the presence of adversarial. She is broadly interested in a number of topics in learning theory, for example, non-parametric method, online learning, and active learning. She is a recipient of NSF Career Award, Hellman Faculty Fellowship, and the Google and Bloomberg Faculty Award. And I also want to mention that Kamalika serves as the program chair of SML, the very prestigious conference in machine learning, SML 2019. And she's going to serve as the general chair of SML 22nd. Okay, so please join me in welcoming Kamalika to give the talk.
Thank you, Kwan, for inviting me. So what I'm going to talk about is, this is just some results of some work that we've been kind of doing in my group. So here is kind of a broad overview of what we do, right? So if you open any machine learning textbook, this is the picture that you see, right? So you have some training data, and then this training data is fed into a in a machine learning algorithm and comes out a classifier, and then this classifier is evaluated on test data, right? And this training and test data are independent samples which are drawn from an underlying data distribution, right? So the training and test data are connected in the sense that these are IID samples that come from the same underlying data distribution. And then if you get high test accuracy, right, which is your classifier predicts the test examples, most of the test examples correctly, then this is a good classifier, right? And this is kind of the the textbook machine learning setting, right? Like if you open the first machine learning textbook, this is the first setting that you see. Okay. Reality, however, is a lot more complicated, right? In reality, there is test and training data never come from the same distribution, right? And in fact, there are a whole bunch of other issues that pop up if you try to get, machine learning methods that actually deploy, right? Machine learning systems that actually deploy to real applications. So there are issues like, robustness. Your method has to be robust to small changes in the test input. Then there are issues like sample selection bias because, most likely you collected data in a specific manner and maybe your data collection was not diverse enough, right? So maybe you didn't touch certain parts of the sample, certain parts of the space or certain kinds of inputs, or you have a biased view of, or you have too many examples of other kinds of inputs and so on. A lot of machine learning is also done on personal data, so their privacy is an issue, and various other things, right? So interpretability, fairness, there's all kinds of issues. And what my group works on, and what we've been doing for the last several years, is this is kind of the domain where we work on, right? So we are interested in by training, I'm basically a theory person, so we look at the foundations of things of this nature, of robustness, this kind of sample selection bias. So we've been working on learning under privacy for a long time. So this is this is a broad overview of of what we've been doing. Okay, and today what we will do, what I'll do is I'll talk about kind of two of these practical issues that my group has been looking at. So one is robustness and the other is overfitting. Okay. So what do I mean by robustness? So I think most of you, especially since you are in the same department as I think Kwan and Chaudhuri, right? Most of you guys have seen this demo. So this is a picture of what is called an adversarial example. So what is going on here? So what is going on here is that people discovered that even slightly perturbing, natural test inputs could make state-of-the-art neural networks give completely, I don't want to use the word random, but like completely arbitrary answers, right? And here's an example of this kind of thing. So you had this image of panda, which you have on the left, right? And it looks like a pretty, it looks like a pretty decent panda, nothing unusual about it. And then you add 0.007 times this thing, right? Which looks like which kind of, to me at least, it looks like garbage, right? Like it looks like random noise to me. And then a neural network, which has been, which classified the panda correctly, now is highly confident that, the resulting image, which, to me at least still looks like a panda, it's completely convinced that this is a gibbon, right? And so these are small perturbations to legitimate, to natural inputs, which can cause a lot of machine learning classifiers to drastically misclassify. Okay, and this can also lead to serious safety issues. So, for example, instead of classifying pandas, if you were looking to classify like street signs, right, and you had you had an autonomous car, and there was a stop sign, and maybe that stop sign had some weird weird feature, and then you classified it as a yield sign, that could lead to accidents, right, for example. And in fact, I'm not showing this here, but there are some people who have come up with a demo like this, right? So they have the stop sign, and they have strategically placed stickers on the stop sign, so that if you just if you have a camera, and if you take images from various angles, from all of these angles, will classify it as a as a different street sign, right? So this can be done in practice. Okay, and so what is known about adversarial examples? Well, there are a very large number of attacks, and the attacks are, by attacks I mean the ways to find these examples that the machine learning classifiers fail on, and the attacks are excellent, right? Like they're extremely good. There are also quite a few, there are also quite a few defenses. The defenses are also quite good. However, there is a limited amount of understanding about why, what is going on here, and why these adversarial examples are cropping up, what's happening. And that's kind of where our work fits in, right? So what I'm going to talk about today is, why do we have adversarial examples? Okay. So let me start out with a little bit of background. So the kind of problem that we are looking at is classification. So what is classification? You are given, xi, yi pairs, where xi's are, vectors of features, and yi's are discrete labels. And your goal is to find a prediction rule that will predict the y's from the x's, right? So as an example, in our this panda gibbon problem that we talked about, your x's are, you take these images and convert them somehow into vectors of features, maybe, vectors of pixel values. Then you come up, and then what you want is a prediction rule that will predict what is in the, what object is in this image. Okay. And this kind of basic textbook machine learning operates from something called the statistical learning framework, right? So this is kind of the basic, theoretical framework that underlies machine learning. So there, so if you formalize it, there the idea is that the training and test data are all drawn, independently from this underlying distribution, and the goal is to find a classifier F that would maximize the accuracy, right? And what do I mean by accuracy? Well, accuracy is if you draw XY pairs from this underlying data distribution, then what is the fraction of times F of X is equal to Y, right? What is the fraction of times you predict the right thing? Okay. Okay. So what about robustness, right? So how do we get to robustness? I think I have a question over here, right? So go ahead.
Yeah, the question is exactly your next slide, which is essentially we cannot solve the problem in my mind if the examples that we take are not essentially embedded in the neural net like words like coding. In coding, we take words, messages, and we put them at some distance from each other, and then the decoding is finding something which is not the message by finding closest neighbor. Okay, right. So this is in some way, if you want to solve the problem of robustness, it sounds like the first thing you have to assume is that there is a way to embed the examples as code words that are far from each other.
Right.
But
excellent. That is exactly my point. So in fact, we will see this as we go ahead. So what you are saying is that in some sense, this is a large margin problem, right? Like you want your decision boundary to describe.
And I heard the argument that any neural net, you have to, it's inherent in the neural net that two things will be close to each other as you wish. And therefore you can always disturb it.
Right. So I think, you know, I mean, yeah, I don't want to give out spoilers, but we'll come to this point in just a little bit.
Okay, go on.
Good movie doesn't give out spoilers, right? Okay, so that was a very, you know, that was an absolutely excellent point raised. So coming back to this, you know, so we are talking about this robustness. So what do we mean by robustness, right? So here is how we are going to define robustness. So to define robustness, we need like a radius. So we are going to talk about a radius, and we are also going to talk about a distance metric, right? So we'll say that a classifier F is robust at radius S at a particular point X, if for this distance metric D, for all points that are within distance S of this X, it's going to predict the same value, right? So, you know, if you look at, as a toy example, if you look at this linear classified, which is the blue line, and, you know, if you imagine either those gray points or those red points, and, you know, and you can see there are these little balls around them, right? So imagine if these balls are of radius X, radius S, then, you know, it's going to be robust at those points, right? Because these balls are all on one side of the blue thing, right? They don't cross over on the other side, right? So this is going to be robust. And when I say that it's robust, what I mean is that this implies that there is no adversarial example around X, right? So that's what you get from robust. And then it's not, you know, I mean, if I want a classifier that's robust all the time, I could just always predict 0, right? And I would be perfectly robust, but I would also be perfectly useless. So what you want is something that combines robustness and accuracy. And we call this measure, you know, it's a form of robust loss, and we kind of gave a name to it. So we called it astuteness. So the astuteness of a classifier F at a radius R is essentially the fraction of points according to this data distribution where you predict the right label. So f of x is equal to y, and also you are robust at in a ball of radius r, right? So you are robust and you are accurate, right? So that's when you're astute. And essentially the goal of robust classification would be to maximize astuteness, right? You don't just care about maximizing accuracy or robustness in isolation, but what you want to maximize is astuteness, okay? So that's kind of the overall goal. Okay. So now let's take a look at why would we even have adversarial examples, right? So what could be some plausible reasons? One plausible reasons could be that data distributions overlap, right? So maybe, you know, like pandas look a lot like gibbons, right? Or maybe dogs look a lot like cats, right? You know, and we don't really know. Another plausible examples is that, you know, maybe the data distributions don't really overlap, but we have too few samples, right? So our classifiers are all based on, you know, very few samples, and, you know, they may be okay to get accuracy, but maybe not okay to get robustness. And finally, what may have happened is that we may be using the wrong algorithm to train our classifiers, to build our classifiers. And, you know, maybe if we use the right algorithm, we would get something that is more robust. But, you know, because we are using a bad algorithm, that doesn't quite happen, right? And I'll give you the answer a little bit. I'll give you a little bit of a spoiler ahead of time. So the answer is, it's essentially number 3, right? In a lot of cases, it's just essentially number 3. And for the next few, you know, the next few minutes, we'll talk about why that is the case. Okay. So we'll begin by looking at, you know, non-parametric methods. I see a question. Yes, go ahead, please.
Yes, my question is the definition of the astuteness.
Mhm.
in the sense that somehow it seems to be a little bit very sensitive to the concentration of the sample points, in the sense that if I have a very concentrated region where I happen to have just one data point, which is outlier, right?
Right.
In that case, that data point will essentially set the probability to 0 around that region, because within that ball, that concentrated region, because of that one outlier, that probability is 0,
Oh, so
isn't it?
Astuteness is a property of a classifier, right? So if your classifier classifies a lot of region around, a large region around it correctly, then you are set, right? So what this is saying is, what is the fraction of points where I predict a right label and I predict the same label in a ball of radius r?
Right. But what I'm a little bit concerned about is that it's not an existential thing. It's for everything it's a universal quantifier. So if there is just one single data point that I actually somehow perturbs things, then that entire region is contaminated because of the universal quantifier.
Right,
And that will set the probability to 0 because I'm universally quantifying it.
right.
So, but when I think about it, that single
But if you have
outlier,
a classifier, right? If you have a classifier which has kind of a stable decision region, that wouldn't be a problem. So it is a problem for things like, classifiers that get more and more local. I mean, unless you do things in a certain way. But, if you have like a classifier which has these decision regions, this kind of, what should I say, big continuous decision regions, that wouldn't be a problem.
thank you.
Okay. Okay. So, so the next thing that we'll be looking at would be non-parametric methods. So, what are some examples of non-parametric methods? One would be, an example is, k nearest neighbor classifiers, where you look at the k neighbors, k closest points to a particular, test example, and you output the majority, right? Or decision trees, everybody is familiar with decision trees, but there are other kind of things as well, right? So for example, random forests or kernel classifiers, they all fall into this non-parametric methods. Okay. So what is known about these non-parametric methods? Before I can talk about that, let's quickly talk about the Bayes optimal classifier, right? So the Bayes optimal classifier, I'm sure most of you have seen this before, but this is the classifier which has the highest accuracy on the data distribution, right? And this classifier is also reachable only in the infinite sample limit, right? So in the finite sample, you would never get to it because you never know exactly the data distribution. But as n tends to infinity, you can hope to reach. Okay. So what is known about parametric methods? So this is a theorem by Stone in 1977, and that was, believe it or not, that was before I was born. Let alone my students. So what the theorem says is that as the training data size grows, the accuracy of many of these non-parametric methods, so I'm just kind of sweeping a bunch of things under the rug here, but the accuracy of many non-parametric methods will converge to the accuracy of the Bayes optimal, provided the parameters are set in certain ways, right? So this is kind of a classical theorem. However, this does not apply to robustness, right? So this is just something about accuracies. Okay. What about robustness? So to understand this, let us first look at robustness for data that is. What do we mean by separated data? As it happens, this kind of the notion of robustness that I talked about a little bit earlier, the relevant definition of separation that is something separation, and is separated if for any x 2 points x y and x prime y prime that are drawn from this distribution, if y is not equal to y prime, then the distance between x and x prime is greater than equal to twice r, right? So what this means is that points with different labels are at least distance 2r apart. Okay. Why is this R separation interesting? The reason why it is R separation interesting, because if the R separation condition holds, then there exists a perfectly astute classifier at radius r, right? So this is kind of the analog of the realizability condition. For for accuracy, we have this notion that there is a perfect classifier. For robustness, this is the this is the right notion under which there is a perfect classifier. Okay. So okay, so that's good. But what would be the limit of robust classification? So how we talked about the limit of accurate classification is the Bayes optimal, right? So that is the most accurate that we could do on a data distribution. Well, what about robustness? The Bayes optimal, so the problem with the Bayes optimal is that it is going to be undefined outside the data distribution, right? So as a concrete example, if, imagine your data distribution of a bunch of red region and a bunch of gray points, and which are, which maybe are separated, then any of these blue lines could be a Bayes optimal, right? Because the Bayes optimal doesn't specify, when we define the Bayes optimal, we don't specify what would happen outside the support, right? However, if you look closely, not all of them are robust, right? And so what we need is a different limit object, right? What we need is a different an analog of the Bayes optimal, which should be the limit of robust classification, and we call R optimal. Okay, so R optimal is the classifier that maximizes astuteness, and for our separated data, we can so this would be one R optimal. I mean, the R optimal isn't unique, just as the Bayes optimal is not unique. So this would be one R optimal, and there could be many others as well. So for our separated data, imagine you have a classifier that predicts plus if you are within distance r of the support of the pluses, and it predicts minus otherwise, right? So let's say we are looking at binary classification. This would be an R optimal, but again, this is not the only one. So this would be an R optimal. And in the general case, when data is not R separated, you can define it as well, but it's it's going to be a bit more complicated, right? So this is this is the definition. Okay. So now that we know what to converge to, right? In the before when we cared about accuracy, we were converging to Bayes optimal. Now we want to converge to R optimal, right? So now that we know what to converge to, we can talk about when do we do it, and we actually have a theorem which shows which establishes conditions under which non-parametrics would converge to the R optimal. And the interesting thing is that some things converge to the R optimal in the large sample limit, and other things don't. So in particular, what you find that, nearest neighbors and kernel classifiers, they will converge to the R optimal in the large sample limit, right? So this is for separated data. For R separated data, they would converge to the R optimal, okay? However, there are other things like histograms or decision trees, which would converge to the Bayes optimal, but not to the R optimal. Okay, and so so that is where there is there is a bit of a gap, right? That there are algorithms, if you use them to build classifiers, they would converge to the Bayes optimal, but not to the R optimal. Okay.
So can I ask a question here?
Yes, go ahead. Yes.
Yeah, so in your illustration for the Bayes optimal classifier, there are two decision boundaries because there are two blue curves. So I wonder why.
No. So what I'm saying is that the Bayes optimal, like anything that just predicts plus on the red region and that predicts minus on the gray region is a Bayes optimal.
Oh, okay, I see.
Right, so there would be, so these would be two examples, but there's an infinite number of such curves.
Okay, I see. Okay, thanks.
Right? But not all of them are robust, so that's why it doesn't make sense to just converge to the Bayes optimal in this case.
Right, exactly.
Something a little stronger.
Okay, thanks.
Okay. No, that's an excellent question. Excellent question. Okay, so the interesting thing here is that, as I said, some things would converge to the R optimal in the large sample limit, and some things that converge to a Bayes optimal would not, right? Even for R separated data. And to give you a quick idea of what's going on here, maybe let's look at a quick example, right? So so one of the things that would not is a decision tree, right? And we can show that it wouldn't converge to an R optimal. I mean, in the standard ways of building a decision tree, but it does converge to a Bayes optimal, right? So what happens over here? Well, what happens over here is, imagine this example, right? So where you have, the red points and the gray points, and they're separated by a distance to R, right? So the R separation condition holds. If you built a decision tree, what you would do is you would pick a threshold in the middle, right? Which would be that blue line. And, since your accuracy is 100%, you would be done, right? But notice that this would be accurate, but it would not be robust, right? And there is a robust decision tree, which is this kind of jagged line, right, which goes through. However, the standard algorithms that you have for building decision trees are not going to find it, right? So the standard algorithms that you have are just going to find this middle threshold, and they're going to be done. And so, so that would be it. Okay, so I think there's some questions in the Q&A, right?
Yes, we do have some questions, 2 questions. Yeah.
Let me take a quick look. Yes, so Kirti is asking, nearest neighbor and kernel classifier converge to R optimal as training data increases. That is correct. And this is for R separated data. In the general case, you have to do something else. You have to do some pre-processing, and then it will, and then after that it will converge. Okay. Vikrant is asking, is R a hyperparameter, or is R the output of the algorithm? That's again an excellent question. So R is usually given to you in advance. So in these kinds of problems, what you are asked to do is you are told that, here is a data set, here is R, find the classifier that is robust to radius R. Okay. I see there's another question. Go ahead, please.
Is the theorem that you talked about independent of the metric that is used?
That is an excellent question. So I kind of hit some details. The theorem would hold for, so for nearest neighbor, the metric that you are using has to be the same as the metric in which you are measuring robustness. Mm. And for kernels, the kernel will decay, right? The metric has to decay. It cannot decay too slowly with respect to the metric in which you are measuring robustness.
I see. Thank you.
Okay, so excellent questions. And now the question is, so, remember how we started talking about robustness? Well, what we see over here is that the robustness does depend on the training algorithm, right? So because, you saw there were algorithms like, nearest neighbors or kernel classifiers where, which did converge to the R optimal, whereas there were things which didn't, okay? Okay, so that was for non-parametric methods. And this is the point at which everybody asks me, well, what can you say about neural networks? So I feel like I have to include this in my talk. So what about neural networks? Okay. So in neural networks, so here is the abstraction that we would be talking about. So a neural network computes a function. Let's just say we are talking about, binary classification. So neural network computes a function f of x. And then what the classifier would do is it would output a sign, right? The sign of f of x, okay? And in this case, what would happen is that the robustness would come from local smoothness, right? So if your f is locally smooth along x, around x, right? It's kind of a smooth function, and f of x is bounded away from 0, then f will be also robust at x. Okay. So for neural networks, again, there are a large number of attacks, a few good defenses. I think Quan has, also worked on some of them. And I think in your department, right, Chaudhuri has probably has worked on a bunch of attacks and defenses as well. However, almost all of the defenses show a robustness versus accuracy trade-off, right? So, when they give you robustness with respect to a radius r, they show a decline in the accuracy. And the question that we are going to look at is that, is this trade-off inevitable? And the answer that we have is not, at least not in principle, for real data. Right. And, this kind of ties into Eleazar. I don't know if I'm pronouncing the name correctly, Eleazar's question. Right. So, so what happens? Okay. So what we can show is, remember we had started talking about this R separation condition, which shows that there exists, which shows that there exists there exists at least a classifier, right, that will be robust as well as accurate, right? What we can show is something a little bit more here. So what we can show is that if your data distribution is R separated, then there exists an F, right, a smooth a function F, such that F is locally smooth. And if you round F, it will have accuracy 1 and robustness radius r, right? So what this means is essentially, not only is there there exists a classifier that can give you accuracy and robustness, but there exists a classifier that can be obtained by rounding a smooth function, okay, a locally smooth function. Okay, now, okay, so that is fine, but is real data R separated, right? So that's the real question, because if real data is not R separated, we can't, we can't hope to have robustness and accuracy. Whereas if real data is R separated, this should be possible. So what we did was we looked at a few different data sets, in fact, 4 different data sets that are typically used for adversarial examples experiments. And here's what we found, right? So what we found is that the separation, right, between, so separation is the minimum distance of any 2 points in different classes, that tends to be much higher than the typical robustness radius that is used in the experiments, right? And there are 2 little stars that you can see next to SVHN and restricted ImageNet. So for in there, what happens is SVHN has 2 images which have exactly the same label. Maybe it was a labeling error. So this result is after you remove those 2 images. And similarly with restricted ImageNet, which is a form of ImageNet that people use in these kinds of experiments, there also you have like something like 2 or 3 images like this. And if you remove like, in each case, we removed less than 5 images, let's just say. And then we found that the separation is usually much more than the typical radii used in adversarial example experiments. Okay, I see a question. Somebody raised their hand.
Yes, hi. I guess I have a question about the MNIST and Cypher data. Is it the separation, is it known that there's a classifier that can accurately predict the things at separation? Or like, I guess the question is like, is there a classifier that would get like 100% accuracy on these? And how does that relate to?
Yes, so there exists one, right? So this is kind of an existence proof in some sense, right? There exists one. Now the question is how to find it.
Right. I mean, how do you even calculate that there exists a separation at that radius?
Oh, there is, you can calculate, you can take the data, right? And you can look at the separation between, test training, and so on, right? You can calculate that.
Okay. I see. Okay. Thanks.
Juan has a question, yes?
I have the same question. How do you compute the distance? Is it based on the embedding that we get from the neural network?
No. So, okay, this is an excellent question. So the distance is usually in these adversarial example problems, you are already given the metric, and this is the L infinity metric. Oh, we have a new guest. Hi. So this is the L infinity metric, right? So, and this is given to you in the problem. So now there's a lot of question about whether this should be the right metric or not. That's, those are all extremely valid questions, right? I mean, people have also looked at perceptual metrics and so on. But in this particular case, this is the kind of most common, most common case. And this is the L infinity metric.
Hi, can you hear me?
Yeah.
It's a great talk, and my question is like, because this separation is measured only on the data set, but the data set doesn't really reflect the true distribution of the data, right? For example, for MNIST, I can take a image of maybe image of digit 1, and maybe I can change it just a little bit to change it to a digit 7 or something like that. And I can definitely do much better than this 0.74 here for the separation
Right.
between the two.
So you are absolutely right that it doesn't change the right. You are absolutely right that what we are measuring is with respect to the data set, and we can never measure it with respect to the distribution, right? Like,
Yeah.
because we don't have access to the distribution. You're absolutely right. However, one thing to notice is, I mean, there could be like really bad 7s which look just like 1s, right?
Yeah.
But they don't show up in your MNIST test examples. So in your MNIST test examples are, in fact, there exists something that would separate, that would classify your MNIST test examples with a large radius.
Yeah, I think the question is more like, at least on this training data set, we still even cannot get a cutter just fitting the training data set with the separation, even not considering like other like edge cases or test sets. Even on the training data set, I think the 0.74 is very difficult for any robust classifier to achieve.
Right. No, that is definitely true. That is definitely true. Right. So this is, this is an excellent point, because this comes to my next point, which is that the real reason why robustness is kind of hard for neural networks is because it's hard to find these classifiers. It's not just that they don't exist. It's just that the algorithms that we are looking at are, they're not really, they're not like generalizing robustly, so to speak, right? So the problem is not so much the existence. There was, in this area, there's been some debate about whether robustness should be at odds with accuracy. And there's been some people who've been saying that, it should be at odds because, you're doing other things. But in fact, so the point of this paper is kind of that in practice for real data, robustness and accuracy are at least both achievable, at least in principle, right? And the reason there is a gap, and the reason why there is a gap is because of what we find is that it's really that we don't have the right algorithms, and the algorithms that we have currently do not generalize as well. So that is kind of the area that one should look at if we are looking to make progress here. Okay.
Yeah, thank you.
So to understand what accounts for this gap, again, what we did was we looked at a quick empirical study. We took these 4 standard image data sets, 7 models, a few different training methods, and we looked at measuring local smoothness, accuracy, and adversarial accuracy. And what we found overall is that, it can sort of be summarized in this particular way. So there are certain methods where the accuracy is, that are not very smooth, right? So here, Lipschitz constant means less smooth. So these are things like natural training. There is something called locally linear regularization, which is, it's one of them. So these are methods where what is happening is that the Lipschitz constant is very high, which means that these methods are not very smooth. They're less smooth, but they're more accurate. Whereas on the other hand, if you look at the standard, some of the standard methods that people look at for training, at robust classifiers, there is something called adversarial training, something called traits, and then there's this robust self-training, right? So these are, kind of the 3 methods. And what happens is in these methods, if you look closely, the Lipschitz constant is much smaller, which means that these are smoother. These give rise to smoother classifiers. But the generalization gap is much larger, right? And so if you look closely, the generalization gap in the red column, in the red rows, it's something like, 6, 9 for accuracy, and then for adversarial accuracy is like 0 or 5. Whereas for these methods, the generalization gaps are much higher. Okay. So what we see is that these smoother methods may be more robust than the less smooth methods. However, they have a large generalization gap. And so, what this essentially means is that, so with neural networks, essentially what is going on is that the data is R separated. So what that implies is that robust and accurate networks exist. However, the problem is that our current algorithms do not find them, right? And it's possibly because they don't generalize well enough, right? They have large generalization gaps. And what this means is that this is kind of in the area where future research should focus on, right? To look at, what makes them generalize better. Maybe what they need is different architectures, because mostly we are using the same architectures that we use for high accuracy. Maybe what they need is better optimization methods, because we essentially use the same SGD and Adam. Maybe you need different optimization methods. Maybe it's something else. Okay, so that's kind of that concludes this part of this talk. So in summary, we should look at robustness for our separated data, right? Because that's when robust and accurate classifiers exist. And it depends on the training algorithm, right? And there are these two kinds of behaviors where, so one would be nearest neighbors or SVM, where, we are just getting this kind of large margin solutions. Whereas for things like neural networks, we are mostly not getting these large margin solutions, okay? Okay, I think John has another question. Go ahead.
So if I kind of summarize what I learned from it, can I say that this is really about the existence proof, in the sense that if the data is all separated, then there exists a function that somehow gives a very nice classifier. But it is not really a constructive proof, in the sense that it doesn't give me an algorithm how to find it, or what are the class of functions that somehow will give this nice separation. So that one is more of like practical work that we have to figure out.
Right. Well, for nearest neighbors and so on, we do show that certain algorithms find it, right? Like that's our ICML paper where we show nearest neighbors and kernel classifiers will find it in the large sample limit.
Oh, so that one, could you kind of maybe summarize exactly what is the proof there then? So does it mean that when the sample data that I train on is R separated, those algorithms are guaranteed to converge to?
Yes, so it's an analog of Stone's theorem. So Stone's theorem says that as n goes to infinity, certain non-parametric, under certain conditions, they are guaranteed to converge. As n tends to infinity, it converges to the base optimal. What our ICML 2020 paper says is that certain other algorithms will converge to the R optimal, right? And that includes nearest neighbors and kernel classifiers.
So that is the large sample convergence.
That's the large sample.
Large sample convergence. Okay, so that kind of, okay. Thank you.
Yes, for neural networks, we can't say anything, you're right. But for those things, we can. Okay, so I don't know. I mean, I could also conclude here, by the way, because there were a lot of questions, which was fantastic. But I might be running short of time. So what should I do?
Oh,
I mean,
no, you have enough time. So yeah, if you have more materials, feel free to, yeah.
No, please keep the questions coming. It's good. Especially in an online talk, it's good to get questions.
Yeah, and we also started a little bit later, so you have more time. Yeah.
Okay, wonderful. Okay, so now what I will do is I will just kind of abandon robustness and kind of move to the second part of my talk, which is about overfitting in deep generative models. Okay, so deep generative models have been, immensely successful. As we have all seen, so there, so these are some examples of natural images that were generated by these models. But the question that we are looking at is, what about overfitting, right? So whether they overfit. Okay, and before we can get to whether they overfit, the real question is, what does overfitting mean? Okay. So, we are kind of motivated by certain kind of examples. So one example would be where, clear overfitting is happening would be, let's say you have a generative model. And what this model does is that it just completely reproduces its training data, right? So every time you ask it for a sample, what it does is it draws a random training point and it releases it, right? And, this would be kind of a privacy concern, right? Especially if you were doing it for healthcare applications, you had a generative model which would give you synthetic data, and if it was just kind of outputting real patients, that wouldn't be kind of a good thing, right? So that would be an example. And so these are the sort of things that we are trying to catch, right? So this would be an example where we want our algorithm to say, okay, there's overfitting. Okay, so let's start out with the setting and the classical view, right? So the setting here is that we have a bunch of training data. And based on this training data, what we do is we build a generative model. From this model, we can generate some data. So we can sample a bunch of points from this generative model. And then we can also have some test data drawn from the same training distribution, and combining the generated data, combining, some function of this generated data, this test data, and the training data, we can calculate an evaluation score. Okay, and here the idea is that this training and test data that we had, these are drawn again, this is a statistical learning framework, so these are drawn IID from the same distribution. Okay, and the classical view of overfitting always has kind of looked like this. On the x-axis, you have model complexity, and on the y-axis, you have likelihood, right? And so what you are doing here is the red line is the training likelihood, or the likelihood of the training data. Likelihood is probability of data given model of the training data. As you make your models more and more complex, if you're doing your training right, then this likelihood will go up, right? The training data will become more and more likely. For test data, what would happen is that the likelihood will go up, and at some point it will start going down, right? This is kind of the classical view. And overfitting happens when there's a gap in these likelihoods, right? So when the probability of, the likelihood of training data given model is much greater than the likelihood of test data given model, right? So that's when you are fitting features of the training data and you're not really generalizing, okay? However, the problem is that, so this is kind of a very nice classical view. The problem, however, is that, this kind of test, it's very hard to do for a number of these kinds of deep generative models applications, right? So in some cases, the likelihood might be hard to calculate, like, VAEs. Or in things like GANs, there's no likelihood, right? All you get is a bunch of samples, and it's just I mean, there are some ways of imposing a likelihood on the GANs, but it's unclear what they mean, and it's not always a straightforward solution. And in these cases also, I mean, overfitting is a serious concern, right? Because these models are built on huge data sets. You can never go over the entire training data, right? There are all these I don't know if you guys have seen, there are all these websites which say this person is does not exist, right? But I often wonder if that person really doesn't exist, right? So these are people who have been generated by GANs, but I often wonder if they really don't exist or if they are copies from the training data, right? You never know, right? Because nobody has gone over this huge training data sets, right? So overfitting is actually a serious concern over here. So what we will do next is we will look at how to define overfitting, and then we'll propose a test for overfitting that we can do based on these, based simply on samples, okay? So when we started looking at this problem, one of the first things we realized is that there are actually two somewhat orthogonal notions of overfitting, okay? And we are going to call them overrepresentation and data copying. So the data copying, this name is thanks to my student Casey, who came up with the name data copying, okay? So what does overrepresentation mean? Suppose you have a training, suppose you have this data distribution and you have a generated sample, right? And, if you take a certain region, right, like a big enough region of space, then you are getting overrepresentation there if your generated samples are much more frequent in that area than, a random test sample. Right. So, for example, maybe you fit cats and dogs, and somehow you just happen to generate dogs almost all the time. Right. So, in your data, in your test or your training, you had like 50-50 cats and dogs. And now somehow your model is such that 90% of the time you generate cats. Right. That would be overrepresentation. Okay. A slightly different and orthogonal kind of overfitting is something we call data copying. So what does data copying mean? So there is data copying. So here, in addition to this training data, generated data, and test data, you also need a distance metric D. And data copying happens in a region C if, on an average, the distance between a generated point and its closest training point is much smaller than the distance between a random test sample and its closest training point, right? So an example of this would be, an extreme example of this would be when you just spit out your training samples, right? Then the distance between your generated points and your closest training point is 0, but a random test sample is somewhat different, right? But this is kind of, so that's an extreme example, but, this definition also takes care of things that are not as extreme. Okay, so you could be, really close to a training point, right? So maybe if you had this, this example of faces that I just talked about, maybe you change a little bit, maybe you change, I don't know, maybe you change something about the glasses and then then that's it, right? So that would be another example, right? And just to make the point that overrepresentation and data copying are two completely different things, you can have overrepresentation with no data copying and vice versa, right? So for example, if you have a mixture of 3 Gaussians was your data distribution, and somehow you model 2, but you drop the third, then that would be overrepresentation, but that wouldn't really be data copying because you're modeling 2 of them very well, right? Whereas if you spit out, let's say, just your training points or, minor variations of training points, you would still you would be data copying, right? Because you are essentially spitting out the training points, but you would, not be overrepresenting, because if you look at, large enough regions of space, well, your statistics overall, the fraction of points from each, large enough region is more or less the same, right? So you would be fine in terms of overrepresentation, but you may be data copying. Okay. So currently, there are a lot of hypothesis tests for detecting overfitting in generative models. There's many. I mean, these are just 5, but I have missed a lot, right? This is a very active area. One of the first things we realized when we started looking at the problem is that almost all of them detect overrepresentation. So they test for overrepresentation, and in fact, most of them, except for one test, right? Other than just one test, almost all of them also fail to detect even exact data copying, right? So even a generative model that just spits out the training data, almost all of these methods would fail to detect. Okay. So now what we will do is we will go ahead and look at a simple test for data copying. Okay. So what would be kind of the simplest thing you can think of for data copying? Well, the simplest thing would be to start with just a test with just the definition, right? So what you do is, you have, you look at the average distance between each test point and its closest training point. Then you look at the average distance between the generated points and their closest training points. And then you test to see if this is greater than or equal to 0. And you can put in, the various confidence intervals, and, you can do the math, and, this test would work out. Okay. A problem with this, however, is that these distances can be large, right? And if you have some outliers, you can end up getting high variance from them. Okay. And as it happens, there are some relatively nice solutions for that. And the solution is to use, instead of distances, is to use comparisons, right? So you are testing if on an average, is the distance between each, on an average, is the distance are test points closer to the training points than they are to, or rather are test points farther from their closest training points than our generated points, right? That's kind of what you're testing. And as it happens, if you squint at it long enough, what you realize is that this is essentially the Mann-Whitney test. It's a very standard, non-parametrics test in like stat 001 or something, right? The Mann-Whitney test on distances between the test points and their closest training points and the generated points and their closest training points, right? So if you could get these distances, you could carry out this test. And the Mann-Whitney test would have much lower variance than if you did the test directly on the distances. Okay, so this is, kind of one idea. Okay. The second issue here is heterogeneity, right? So, these deep generative models, they are in fact extremely heterogeneous, right? So, there would be some regions where they would data copy, there would be other regions where they would not do anything at all, there would be other regions where they would, kind of underfit. And so if you have global tests, what's going to happen is that the global test will not work for these kinds of heterogeneous models, right? And so the question is how to account for this heterogeneity. Okay. And what we do is we again use kind of a standard, it's kind of a standard tool in the kind of toolboxes people who worked on these kinds of classical non-parametric methods looked at, which was just, binning or dividing the space up into cells. And so that's what we do. We divide, so we look at the entire, input space, we divide them into cells. Usually we do this in, using a validation set, using some clustering on the validation set, and we divide it into cells, and then we do our test in each cell, and then report the weighted average of the one-sided test results. And if the weighted average looks looks high, then we can go and look inside each of the cells, and then see if the test failed in them. Okay, so that is basically our test. And now the question is, how well does it detect data copying? Okay. So I'll talk about, kind of two of our experiments. So one was we looked at VAEs on MNIST. And in VAEs, what happens is variation autoencoders, you can vary the latent dimension from 1, where it like really underfits, to 100 overfit, right? And what people have done before is, they didn't test for data copying, but generally people believe that when you're at 100, what is happening is that there's a lot of memorization type of stuff happening, right? This is something that people believed before. And the metric D that we use is the 64-dimensional latent space of an autoencoder, which was trained with a VGGNet perceptual loss. So this is kind of a standard, metric that people use for MNIST on VAEs. Okay. And here is kind of what we see. So in all cases, the x-axis is going from overfit to underfit, right? And what we are plotting is the value of a test statistic, right? And our test statistic is the CT, the one on the right side. And we have two other test statistics. So one is called the two sample nearest neighbor test. So this was due to Lopez Paz and Okwab from 2016. And so these are, the 3 lines are 3 variants of the test. So this is the only test that I said that is capable of detecting exact data copying, right? So this is a test that's capable of detecting exact, not really approximate, but more, exact data copying it can detect, okay? Then the second one, the one down below, that is the generalization gap. So notice that for VAEs, we can't really calculate the, we can't really calculate the likelihood. So we look at the elbow, which is kind of an approximation to the likelihood, and look at the generalization gap based on that. And what we find is that is again, not a good indicator, because that goes straight, then goes down, goes flat, goes down, goes up, and then goes like this, right? Whereas in our case, what is happening is that the line, right, the test statistic, as we go from overfit to underfit, the test statistic goes up, goes up straight, right? It goes up, and the dotted line is where the perfect fit line is, right? So at the dashed line is where the perfect fit line is, right? So what you see is that the perfect fitting is happening sometime around the dimension 40, and then the statistic goes up. For the two sample nearest neighbor statistic, according to their theory, the dashed line again is where the perfect fitting should happen. And so what they are showing is, what they are claiming is that they're always underfitting. So so they do show an upward movement, but the calibration is not quite right in this case. Okay. Then the second kind of experiment that we did was with Big GAN, which is this huge GAN which is trained on ImageNet. Now we cannot train Big GAN. We are like a small academic group. We don't have the resources to train Big GAN. So what we did was we looked at, we got like the Big GAN off the internet. And then we looked at 3 classes, and ImageNet has its own test set. So we looked at 3 classes from that test set. And these 3 classes, like 2 of them are the default classes for Big GAN. I think Coffee and Bubble are default classes for Big GAN. So if you get the Big GAN thing in PyTorch, then those are the 2 classes that you can test things on. And then Schooner is my student randomly picked a class out of the rest. So this was a class where there was an object in the foreground. So he randomly picked a class where there was an object in the foreground. Okay. And for Big GAN, what happens is, since we can't retrain it, we can't really, do overfitting to underfitting. But they have a parameter called the truncation threshold, and which they claim controls the sample diversity. So if it's a high truncation threshold, then you should get a lot of different samples. So whereas if you have a low truncation threshold, then your sample diversity is very low. So that's kind of overfitting. Whereas, and the other cases when the truncation threshold is high, that means high diversity. And the metric D that we used was the 64-dimensional PCA of the inception space, which is again a standard thing in this case. And approximately, here is what we found. So again, here we cannot do the generalization gap because we just have samples, we don't have likelihoods. But we can do that nearest neighbor test and our test CT. So in the nearest neighbor test, what you can see is as you vary the truncation threshold, these lines just stay more or less constant, right? And these 3 lines, the nearest neighbor thing is on the left, and these 3 lines are 3 variants of the test. The different colors are the different variants of the test, and then the 3 different lines are the 3 different classes. Okay, I think the diamond is Bubble, the dot is Coffee, and the triangle is Schooner, right? So these are 3 different classes. Whereas our test, our test metric, if you look at it, as the truncation threshold goes up from overfit to underfit, our test metric also goes up, right? It tracks the fact that the samples are getting more and more diverse, right? And there's at some point where it crosses the perfect fitting threshold. I don't know what that means, but it does seem to track this upward trend. And just to give you a sense of what is it that we are seeing, so these are some random samples drawn from 2 cells, right? So the first one is the top one is a data copied cell where the real are these are some test examples, and you can see there are different kinds of coffee cups, whereas the generated samples, if you see, it's kind of images of very similar coffee cups being generated over and over again, right? Like this is like the image 1, 2, and 3 are essentially the same coffee cup from slightly different angles, right? Whereas if you look at a non-data copied cell, as predicted by your test, if you look at test points from that cell versus generated points from that cell, the generated points are actually a lot more diverse, right? So they're not like, the same coffee cup being generated over and over again. So our test is, it seems to make sense, right? This is like a broad sanity check, right? So in conclusion, what we looked at is, we talked about, 2 notions of overfitting, and, we proposed a test for data copying. So data copying was, before this, it was just, sort of being ignored. So we kind of formalized that there are 2 somewhat orthogonal notions, and here's a test. And I think the real question moving forward is what are some other notions of generalization in deep generative models, right? Because it's what is getting very clear is that generalization there is not as simple, right? It's not simple as training versus test likelihood. There are more things at play, and are there other interesting things? Okay. And so again, these are just some references. The first three are for our robustness, our papers on robustness. And the last one is our paper on data copying. And finally, I would end with, pictures of all the people who did the work. So there are my students, Yaoyan, Ishan. Ishan has already graduated, Roby and Casey. And Cyrus is a postdoc at UCSD. So he's on the job market this year. He's very good. And then my collaborators are Shanja and Russ. And with that, I'll take any final questions if there are any.
Yeah, thank you for the great talk. Now let's take more questions. I think that there are already 2 questions in Q&A.
Oh, on the Q&A, oh, okay.
Yeah, it's about perhaps the second part of your talk.
Ah, I see, okay. Wait, oh, these 2 were answered. Open ones, okay, good. Wow, this Q&A thing is kind of, how is the distance between images computed, right? So Stephanie is asking, how is the distance between images computed? I see, this is an excellent question. So the test will depend on how the distance is computed. So what we do is we choose distance metrics for more complex things like images. We usually choose distance metrics that make sense. So for example, for the ImageNet experiments, the inception space is a very standard kind of feature space in which people look at images. So we use that. For the MNIST VAEs, this kind of the latent space of an autoencoder is would be something very standard to look at. So that's kind of how we choose it. But you are absolutely right that this distance metric is definitely a parameter in these tests. Yeah, and things will vary. Okay. Akash is asking the distance between data points on MNIST CFAR computed from raw pixel values. Yes, so that is also an excellent question. So if you compute a distance from raw pixel values, that will not give you very good answers. And the reason for that is that, in MNIST, if you, for example, if you shift the images a little, the distance will become very high, right? So the distance from raw pixel values will not, and you will have to, select these kinds of feature spaces.
Yes. So actually, I do have 2 questions. The first question is about the smoothness. So basically, there is experiments you have shown in your talk. The larger the Lipschitz parameter, the less smooth. The smaller the Lipschitz parameter, the more smooth.
Right.
And so I might misunderstand it, but my understanding is that Lipschitz parameter is not gradient Lipschitz, right? It's a function.
Right. So that Lipschitz, that's an excellent question. So the question is, how do we compute this? So you can't really exactly calculate it. So the way we calculate it is using a PGD-based attack.
Oh, I see.
Yeah. So you can't exactly calculate it. I think there are ways of upper and lower bounding it now. There might be like newer methods that upper and lower bounded. So what we do is we use a PGD based attack, and then the attack, like the attack PGD that we use is much higher than, it's a much more powerful attack than the one we used to train. Which
okay, I see. Okay. And my second question is about, because in the last section of your talk, you proposed 3 two-sample test algorithms.
Right.
In the experiments, I only saw 1. So I wonder what's the performance of the other 2?
No, we have one algorithm. So the algorithm uses these 3 ideas. So one is, instead of the data, going distance-wise, we do this comparison. And then instead of doing a global test, we do local tests. So we have one algorithm that uses these,
Oh, one algorithm uses all 3. Okay, I see. Okay, yeah. Okay, thank you. All right.
Hi, Guy. Good to see you.
Good to see you. Yeah, I really enjoyed this talk. I had a question specifically about the VAE experiment. So I'm trying to understand why the VAE elbow was failing. And so I have 3 hypotheses. Maybe you can tell me which one it is. So it seems that either the true likelihood, which we're approximating here, is somehow not measuring the overfitting. I don't know why. The other option would be that the training likelihood elbow is like not tight, meaning that you're not actually detecting the fact that your training likelihood is much better than it really is. Or it could be that the the way that people estimate the elbow here, which is with importance sampling, just has too high of a variance. And so we're actually getting a very high variance estimate of a lower bound, and we just get garbage. And so, or maybe there's another reason, but I'm trying to understand what is the reason that that elbow is not really measuring overfitting.
That's a very good question. I don't exactly know. I have to look into this a bit. That's a good question. So you're saying that the importance sampling maybe that's possible. I don't know. That's a good question.
I'll send an email to follow up. I'm really curious what's going on there. Yeah.
Sure. I'll also connect you with my student who was looking at the experiments. But you are right. There might be something going on with the yeah.
All right. Thanks.
Over here.
I think we just got one more question in Q&A. It's about again the experiment. I think it's about the notion of separation.
Have you calculated distance between images in the same class, or for different classes will they be different? That's an excellent question. So the distance between, if you look at the distance between images in the same class, those are usually much smaller than the distance to the different class. So it is not true that for every image, its closest image may not belong to the same class, but on an average, they are much closer, right? So for example, if you look at like every image, and if you look at the closest image from the same class versus the closest image from a different class, and if you record their distances, the same class is on an average much closer. But there are points whose closest image belongs to a different class.
Yeah. Any other questions from the panelists or from the attendees? All right. If you don't have questions in the interest of time, let's thank our speaker, Kamalika, again. That's an excellent talk. I really enjoyed. Thank you.
Okay, thank you, guys.
Thank you, everyone, for attending this seminar.
Thank you. Bye.